So, Shunmin is a researcher at Alibaba Cloud and head of network products with extensive expertise in SDN and NFV. He has led the development of Alibaba Cloud's comprehensive cloud networking product line. His most notable achievement is the creation of the Luoshen cloud network platform. And his talk today is also about the Luoshen. Yeah, let's welcome. Yeah, Shunmin.
Okay. Hello, everyone. Thank you for attending my session. My topic is large-scale, high-performance cloud network for public cloud. I'm Shunmin from Alibaba Cloud. Cloud network is a multi-tenant virtualized network based on physical network, providing connectivity for all cloud-based services. The number of VPCs doubled in the past 4 years on Alibaba Cloud. The VPC is the network space for tenant. And we process 15 trillion API calls per day, 1.6 million VMs in a single VPC. And the host network performance increased by 16 times for the past years. Cloud network consists of 3 planes: data plane, control plane, and operation plane. Based on this, a portfolio of network products are provided to tenants. The left side is the cloud network architecture. Data plane processes data packet on devices such as with switch, gateway, and the network function. Control plane controls how network devices behave by providing API to tenants. And the operation plane maintains both control plane and the data plane by monitoring, diagnosis, and upgrade. For the past years, we are struggling with the following challenges in 3 planes. In data plane, we are facing software bottlenecked by CPU, limited hardware table resources, and extreme workload volatility. In control plane, we are facing rapid iterated service on infrequent updated devices, hyperscale configuration management, and the configuration verification overhead. In operation plane, we are facing high frequent topology update, virtual network complexity, and multi-tenancy operation risk. So now let's dive into the data plane. Data plane determines how fast the packets move across the network. To build a high-performance cloud network, we need to accelerate 3 types of network. The first one is host network. Host network provides virtual switch to VMs. Due to CPU limitation, VM network performance is constrained. The challenge is how to overcome the CPU bottleneck in host network. The second is gateway network. Gateway serves a central point to manage traffic in data center. However, the scale of forwarding tables exceeds gateway hardware capacity. The third one is network function. Network function account for the majority of network products for tenants due to workload volatility. Network function cannot meet requirements. So the challenge is how to adapt the workload volatility in network function. Hardware is great at performance, but misses the flexibility of software. Data plane needs to deliver performance and flexibility at the same time. According to our data, the traffic offload ratio by hardware is less than 50%. So the first insight is software and hardware need a co-design to optimize offloading. In the ASIC programmable switch like Tofino, the 60 megabytes on chip memories are very limited. The second insight is that table challenge is about how to compress or split tables in limited on-chip resource. Hardware-based network function is deployed at an interval of weeks to months. So the third insight is efficient resource provisioning would enable network function elasticity. To accelerate host network, we designed Triton, a flexible hardware offloading architecture for vSwitch in Alibaba Cloud. The issue is that existing hardware offloading solutions ignore the programmability gaps between hardware and software. So we designed Triton. Triton leverages the hardware to support the static part of packet processing and the software to cover the flexible part, thereby speed up all types of traffic. Triton greatly improves host network performance. PPS increased by 2.2 times, bandwidth boosts by 3 times, and CPS grew by 1.7 times. To improve gateway performance, we introduced Sailfish, a multi-tenant, multi-service cloud gateway designed with programmable switches. The requirement is that cloud gateway needs to deliver a throughput of over 10 terabits per second with the flexible services. So we designed Sailfish. Sailfish is built on programmable switch. It solves the table resource challenge by horizontal table splitting and single node table compression. Sailfish outperforms x86 gateway in terms of throughput and latency. Its throughput grows by 20 times, and the latency decreased by 20 times. To cope with the workload volatility, we developed CyberStar, a simple, elastic, and cost-effective architecture for network function management. The challenge is that extra CPU cycles and bandwidth consumption in stateful components introduce latency inflation and cannot scale. So we designed CyberStar. CyberStar is a decoupled 3-plane architecture. It utilizes general-purpose VMs to run network workload with flexible deployment. CyberStar can automatically scale to handle millions of connections in minutes. Net throughput grows by 6.7 times. So we have some takeaways in data plane. The first one is that hardware is not the silver bullet. Do not rely on hardware to do everything. Hardware should always provide fallback logic to software processing to avoid unrepairable problems. The second is co-design works when requirements conflict. Use software for flexibility while hardware offloading for performance. The third one is decouple to scale. Separate packet processing from stateful service logic and decouple network function from specific hardware. The second is control plane. Control plane provides API to tenant to control network behavior. To control a larger cloud network, we need to optimize 3 layers in control plane. The first layer is the service layer. Service layer manages different network services that iterate frequently to satisfy customers. The challenge is how to deliver service in a fast pace. The second layer is the device layer. Device layer control device. However, device type varies, such as x86, NFV, and programmable switch. The challenge is how to manage heterogeneous devices. The third layer is configuration layer. Configuration layer manages network configurations. The scale of configuration boosts for the past years. So the challenge is how to handle billions of configurations. Larger scale devices bring hyperscale configurations to control a larger scale network. Service, device, and configuration management need separate solutions. Device control shares a common logic across services that accounts for 20 to 40% of lines of code. So the first insight is device control logic can be consolidated. In a large tenant network, a single ACL rule may be distributed to more than 100,000 servers. The second insight is centralized configuration distribution cannot scale. VPC is the fundamental network for cloud tenants. Configurations are all built into or around the VPC. So the third insight is configuration can be verified through VPC modeling. To control network devices, we designed Poseidon, a consolidated virtual network controller that manages millions of tenants via config tree. The problem is that more than 30 dedicated controllers for different services gain agility, but introduce substantial cost of maintenance. So we designed Poseidon. Poseidon is a partial consolidated architecture. Surface layer consists of individual surfaces for agility. Device layer is consolidated that manages all devices. Poseidon reduces controller OPEX by 41% and improves P99 performance by 73%. To handle configuration scale, we designed Achilles, a mixed SDN mechanism with centralized push and distributed self-learning for cloud networks. The bottleneck is that when distribution scale keeps growing, centralized SDN controller by programming configuration cannot scale. So we design Achilles. Achilles only programs gateway, and let vSwitch actively learns VM location configurations from gateway. Traffic goes via gateway before vSwitch learns rules. Achilles can distribute configurations to vSwitch in a second with less than 4% overhead in extreme case. To reduce the verification overhead, we introduce LF-Vary, a modular and expressive model-based verification for virtual network. The challenge is VPC configuration is error-prone for tenants. A single VPC could contain millions of VM location configuration. So we design LF-Vary. LF-Vary uses an expressive modeling method to verify large-scale VPCs. To improve efficiency, a tree-based structure is developed to store configurations. LF-Vary can model more than 100,000 VPC components and finishes verification in less than half an hour. So we also have some takeaways in control plane. Do a thorough and long-term plan for new system. Test cases are not enough. Infrequently used services may hide bugs. We spent 3 years to migrate all the system to Poseidon. The second takeaway is SDN doesn't have to be centralized. To overcome the limitation of a centralized SDN mode, we use a programmable gateway to relieve controller burden. The third one is corner cases are norms rather than exception. When scale is large enough, corner case will be norms. Device run into bad state for various reasons. Implicit software errors lead to consistency. The third one is operation plane. Reliability is the key factor for tenants to deploy their workloads on cloud network. Operation plane needs to maintain a reliable network through the following steps. The first one is monitoring. Network monitoring collects the network states. Traditional monitoring cannot cover virtual network stack. So the challenge is how to monitor virtual network stack. The second one is diagnosis. Network diagnosis identify network issue. Existing tools fail to give a concrete reason facing the cloud complexity. The challenge is how to diagnose complex paths in cloud. The third one is upgrade. Network is upgraded to deliver features. Tenants' workload should not be interrupted during upgrade. So the challenge is how to minimize customer impact. Tenants update network topology in high frequency, while operation team performs continuous upgrade. Operation plane has to deal with such dynamics. 10 of thousands of topology chains per hour in a typical cloud region. The first insight is telemetry policy must be up to date with tenant topology. Cloud network is a complex system, consists of millions of virtual forwarding devices. So the second insight is diagnosis should be automated to root cause the culprit. A small set of device properties should have strong association with tenant failures. So the third insight is upgrade could use risk relevant properties to contain risk. To measure virtual network stack, we designed DoNet, a proactive telemetry system for cloud networks. The problem is that physical network telemetry fails to detect virtual network stack since there is no precise topology mapping between virtual network and the physical network. So we designed DoNet. DoNet is a cost-effective telemetry on virtual networks, which can handle faster topology updates and achieve tenant oblivious VM to VM telemetry. DoNet reduces 80% telemetry overhead and makes topology update take effect in 6 seconds. To root cause failure, network failure, we develop WeTrace, an automatic diagnostic system utilizing packet coloring and big data processing. The problem is that in cloud networks, diagnosis is slow and inaccurate due to complexity in network stack. So we design WeTrace. WeTrace performs automated low overhead tracing by coloring packets and uses fast slow path architecture to root cause, which cuts diagnosis time from hours to minutes by providing precise, actionable root causes for packet loss. To minimize operation risk, we use Cloud Planner to manage our operation plan, which models each operation task by analyzing tenant impact. The challenge is the massive scale and the property diversity of cloud networks make a virtual device upgrades inherently risky. So we design Cloud Planner. Cloud Planner models upgrade planning as an optimization problem, using a faster heuristic to maximize test coverage of high-risk device properties while minimizing tenant impact. Cloud Planner covers 25% more potential failures than other schemas and cuts tenant risk by 50%. So we also have some takeaways in operation plane. The first one is telemetry is good. Accurate telemetry is great. Telemetry could give us the insight of the network. However, noises could greatly reduce the value. It's key to make telemetry accurate. The second insight is customer impact first. Customer impact is the first thing to consider. Different practices are applied to reduce impact, such as a smaller batch sequential upgrade. The third takeaway is model risk. Don't just react to it. Historic failures are source of model risk. By analyzing failures, we could identify failure triggering properties and optimize model. Based on these works, we have built a large-scale, high-performance cloud network named as Luoshen, servicing millions of tenants on Alibaba Cloud. We have published 48 papers, and 11 of them accepted by SICOM and NSDI. More than 200 patents granted. Alibaba Cloud is one of the world's largest cloud computing companies, providing scalable, secure, and reliable cloud computing services globally. We have 29 public cloud regions, 89 available zones, more than 3,200 CDN nodes, and 180 terabit per second global internet bandwidth. That's all my presentation. Thank you.
Yeah, thanks Shunmin for a great talk. So any question?
Okay, thanks Shunmin for a great talk. I just have a curious question that you talk about a general talent in the cloud, right? So for the AI training or AI inference talent, do they have any special requirement or special challenge in your network?
Okay, so I will ask my colleague to answer your question so he can give you more details.
Okay, yeah,
thank you.
Yeah.
Hi, that's a good question. So actually, in Alibaba we have another well-known technical HBM that is done by another team. That team is working on the GPU cluster and the what you said, the AI networking to accelerate inference and the training part. So what we were talking about here is more fundamental. It's the cloud part that supports like GPU and the general program.
Yeah. For the HBM part, for the physical network part, I fully understand that. My question is for virtual layer, just for what you talk about. For this layer, do they have any special requirement or special challenge?
Cool, yeah. Actually, I can give you one example. For example, when our tenants, they have to deploy their business in different regions, and they have to do some distributed learning and pulling data to do the training. So one challenge we were facing right now, or our tenant brought to us, is to how to accelerate the data transportation from different regions to one location to help them to do all kinds of training. That is a challenge we were facing, and we were trying to do some new feature in our product to accelerate that traffic. So that's just one example. But more than that, we have some thing in the next maybe 2 or 3 months. We have some another talk in a different conference.
Okay. Thank you very much. Yeah.
Okay, if no more questions, I will close this session now, and we can have more discussions in the panel discussion.